Welcome to Everyday Mathematics. Today we move forward to the MIT Integration B regular season 2026 part 2, where we look at problems 11 to 20. These are cool problems. I hope you stick around and see how we may be able to try and solve these problems. Now, as a word of caution, these are our suggested solutions. We've compared with some of the solutions that the answers that we provided. There are areas where we seem to deviate from what they suggested, but this is how we would have solved these problems. Please stick around. This is problem 11, problem 12, 13, 14, 15, 16, 17, 18, 19, and 20. So really cool problems. So stick around and watch how we may be able to solve them. So problem number 11, which happens to be a definite integral from x equals to 0 to x equals to 2026 of the fractional part, where you see those curly brackets, it means the fractional part of x plus a half times the floor function of x over 2 plus a third times the floor function of x over 3 plus a quarter times the floor function of x over 4, and so on and so on and so on. So we see the pattern. Let's see how we may be able to solve this problem. Now, the first thing I would like to do is first begin from the innermost function. So what is a floor function? So a floor function of a value x equals to an integer k, and this x could be also a function fx, let's say fx, but yeah, the floor function of x is equals to k when x is less than k plus 1, or lies between integer k plus 1 and greater or equal to k, right? So that's the floor function. And how you would probably visualize it is that if you have a graph, and here we have floor function of x, we have 1, 2, 3, and so on and so on and so on. From 0 to 1, it's that. From 1 to 2, it jumps up and it goes all the way to 2. From 2 to 3, it jumps up to 2. So we have 2. And so on and so on. So it's a discretized look at the value x. As opposed to, let's say, if fx equals to x, then you have a line that is increasing monotonically or linearly up. So here, that is the floor function of x. What about the fractional part of x? The fractional part of x is equals to x minus the floor function of x, which means that it's always that remainder after every integer value. So if, for example, if you have the same situation where we are looking from 0 to 1, 1 to 2, 1 to 3, we see that from 0 to 1, it increases up to 1, and then it jumps back to 0. Then it increases up to 2, and it jumps back to 0, like that. So in other words, the floor function of, the fractional part of x is less than 1, greater or equal to 0. So it always lies in that region. Now, this is where we are now. So let's see how we may be able to solve with the knowledge of the floor function and the knowledge of the fractional part. How may we be able to solve this integration? So with the knowledge of a floor function and a fractional part of value x, how may we be able to solve this integration? that we have at hand. So 0, 2026 of the fractional part of x plus a half, floor x over 2 plus a third, floor x over 3 plus a quarter, floor x over 4, and so on and so on and so on. How may we be able to solve that? Now, let's I think the important part for us is, since we know that the fractional part of fx, and fx could be whatever is inside this part here, is less than 1 and always equal greater than 0. So this is something to be always cognizant of. A fractional part of a function of x is always lies between 0 and 1. So let's draw a graph, and we say, okay, this is x, and 2026 is our last value there. We have 1, 0 to 1, 1 to 2, 1 to 2 to 3, 2 to 4, and so on, up to 2025, and so on. Okay, so between, when x is between 0 and 1, in other words, this part is going to be 0, 0 over 2, 0 point something, 0.9 over 2. The floor function of that is always going to be equal to 0. And so we are left with our function here being equal to the fractional part of x. From 1 to 2, similarly, 1.0, 1.2, all the way up to 1.9999 divided by 2 is floor function is going to be 0. So everything here decomposes or collapses to 0. So we are left with the floor function of x. I mean the fractional part of x rather. And from 2 to 3, since now this part here, we have 2.0 all the way to 2.999 divided by 2. Floor function is always going to be equal to 1. So from here to here, we have the fractional part of x plus a half. Here, we begin to see that this becomes x plus a half plus a third. And so on and so on and so on. Now, what is interesting is that since our guy here is always going to be between 0 and 1, we're going to put 1 there. And so for x, that's how our integrand is going to look like in that domain. Similarly here, it's going to be equal to that. From here, x plus a half fractional part, we're going to see that when x equals to 2, we're going to have the fractional part being equal to a half. And then at when 2.5 or 2.5 is where this becomes x plus a half equals to 3, so the fractional part becomes 0. So we're going to increase up to that part. And then at 2.5, it jumps back to 0. And at 3, it goes back to a half fractional part. Now, a half plus a third is equals to, I think, 5 over 6, right? So 6, 2 plus, oh no, 3 plus 2, yeah. And so what that means that when x equals to 3, the fractional part is equals to 5 over 6. So we take 5 over 6 here. And then at 1 over 6, 3, 1 over 6, this guy increases up to 1, and then it collapses back to 0. And at 4, it rises back up to there. And so we assume that that is going to be the case for succeeding intervals. So one thing we may want to do is let's divide these domains, right? So I have 1, 2, 3, 4, all the way up to 2026. And we see that the integration is going to be equal to the area under these lines here. The integration is going to be that. Right? And so on and so on. So obviously, as we see here, is that the integration here is going to be the area of this triangle, base 1, height 1, and so half is the area. Similarly here, half. Now for region 3, it's going to be a little bit intricate, but let's say that we know from here to here is 1, from here to here is a half, and this is half. Okay, so we have the trapezium, and then we have the triangle where we have base of half, height of half. So area of 3, let's maybe go back to white, is equals to area of trapezium plus area of triangle, which is equals to a half. A is going to be 1, B is equals to a half, height is equals to a half, plus area of triangle is half times base times height, which is half, half, half. So this is 3 over 2, so we have 3 over 8 plus 1 over 8, which is 4 over 8, which is equals to a half. So in other words, area here is a half as well. And this area also is a half if you try to solve it. And in other words, if 5 here, we're also going to get a half, and here also half. What that means for us is that our integral from 0 to 2026 of the fractional part of x plus a half, the flow of x plus a third, flow of x over 3 plus a quarter, flow of x over 4, and so on and so on and so on, is equals to a half times 2026 slots, which is 1013. And that, ladies and gentlemen, is our answer. So problem number 12 happens to be this indefinite integral. A definite integral from x equals to a half to x equals 2 of x to the 8th over x to the 8th minus x to the 6th plus x to the 4th minus x squared plus 1. So the first thing I will do is just express this in a kind of mixed fraction. So I divide x to the 8th by x to the 8th minus x to the 6th plus x to the 4th minus x squared plus 1. So if we multiply by 1, we get that. And so the remainder just becomes x to the 6th minus x to the 4th minus plus x squared minus 1. And so our integral is the same as is two special integrals. This is simple, but we have x to the 6th, x to the 4th, Okay, and so this is the same as plus, let's call this integral I. And this, as you see here, this is the same as 3 over 2. Now that's 2 minus a half. Is 3 over 2 plus I. So our special integral focus now is going to be I. We're going to figure out what I is, and then move from there. So what is I is okay. Let's divide through by x to the 8th. Okay, both the numerator and the denominator. Okay. It becomes and this becomes 1 minus 1 over x squared plus 1 over x to the 4th So, and then we say let u be equal to 1 over x. What that means is that du dx is equal to negative 1 squared, meaning that negative x squared du is equal to dx, and this here happens to be 1 over u squared, so we have negative du over u squared is equals to dx. Important. Now, what about when x equals to a half? U would be equal to 2. When x equals to 2, u would be equal to a half. And so, in a way, the limits have inverted. But our problem that is now this 1 over x squared minus 1 over x to the 4th plus 1 over x 6th minus 1 over x to the 8th 1 minus 1 over x squared plus 1 over x to the 4th minus 1 over x 6th plus 1 over x 8th. This now becomes 2 to a half of u squared minus u to the 4th plus u to the 6th minus u to the 8th over 1 minus u squared plus u to the 4th minus u to the 6th plus u to the 8th. And then we have, okay, so this here now means that this goes to 0, this goes to 2, this goes to 4, this goes to 6. And so we have negative 2 to a half of 1 minus u squared plus u to the 4th minus u to the 6th. And we have 1 u squared plus u to the 4th minus u to the 6th plus u to the 8th du. So this minus sign has come from here, and it allows us now to invert the limit. So we have a half to 2 of 1 minus u squared plus u to the 4th, so u to the 6th, over 1 minus u squared plus u to the 4th minus u to the 6th plus u to the 8th. So we can pull the negative 1 out and rearrange things. So this integral becomes negative a half to 2 of u to the 6th minus u to the 4th plus u to the 2 minus 1 over u to the 8th u to the 6 plus u to the 4th minus u squared plus 1 du, which is equals to 1/2 to 2x squared minus x to the 4th plus x to the 2 minus 1 over x to the 8th minus x to the 6th plus x to the 4th minus x squared plus 1 dx, which equals to negative I. Now, it is very impossible to say if I equals to, this means I is equals to 0, right? And that means that now our original integral, 1/2 to 2 of x to the 8th over x to the 8th minus x to the 6th plus x to the 4th minus x squared plus 1, which was equals to 3 over 2 plus I, just equals to 3 over 2. Okay, and that's our answer. So problem number 13, that's the indefinite integral of the square of hyperbolic sine of x. I guess the first thing is, let's try to substitute for that and say let u be equal to the arc hyperbolic sine of x. And what does that mean? It means that the hyperbolic sine or sinh of u equals to x, and when you differentiate both sides, you say cos u du dx is equals to 1. In other words, cos of u du is equals to dx. Important step. So our integral now becomes u squared cos u du, which is the same as u squared times the derivative of sinh of u. So going to use integration by parts. And what does integration by parts tell us? That if you have a function that is composed of a product of two functions, v and the derivative of du, when you integrate that, you get the product of u and v minus u times the derivative of function v integral. So we're using that. And we take v to be u squared, and we take u to be sinh u. Okay. So, and then we have u squared okay, right? And we use integration by parts, so uv is equals to u squared sinh of u minus sinh of u times the derivative of u squared. And that means that we have u squared sinh of u minus 2u sinh of u. Again, express it as u times the derivative. Sinh u is the same as the derivative of cos of u. And this becomes, using integration by parts again, we have uv being equal u cos of u minus cos of u times the derivative of u, and that means that we do have u squared sinh of u minus 2, and we do have u cos of u, right, minus the integral of cosh of u. So which is u squared sinh of u minus 2u cosh of u plus 2. Integrating cosh u means we have back to sinh of u plus the integration constant. But since we said sinh of u is equals to x, and u being equal to arc sinh of x, and then cosh of u being equal to 1 plus x squared, then our integral becomes u squared here, and we have x arc sinh of x squared, where this is u squared and this here is sinh u, minus 2 cosh u is the square root of 1 plus x squared. U is arc sinh of x, and then plus 2 sinh u is x plus the integration constant. And that, ladies and gentlemen, is our answer. So this, by the way, is arc sinh of x. Anyway, so that's the answer. If you have any question about that, please reach out to us. Thank you. So problem number 14, which happens to be the indefinite integral of the square of cosine of 2026 x times the cosine of 1013 of x. Now, how can we solve this? I think the important part here is to express this as a non-powered trigonometrical function. I would like to use this identity. So cosine of 2a is equivalent to twice cosine squared of a minus 1, which implies that cosine squared of a equals to a half times cosine of 2a plus 1. So this is the identity I'd like to use. Okay, now, and this is supposed to come in quickly. So our integral now becomes a half cosine of twice 26x, which is 4052 of x, plus 1 times cosine of 1013 of x. So when you multiply that through, we get integral of cosine of 4052 x cosine of 1013 of x plus cosine of 1013 of x. Interestingly, we then have to also separate that, and we know that cosine of a times cosine of b is the same as half cosine of a minus b plus cosine of a plus b. Right? Using that, we can then say that so we said we had our identity. Cosine of a, cosine of b equals to a half cosine of a minus b plus cosine of a plus b. Right. And so our integral, which is a half cosine of 4052x cosine of 1013x cosine of 1000. This is the same as becomes a half, integral of a half. The difference becomes, it's going to go very quickly in there, but is the same as a half cosine of 39x plus cosine of 65x plus cosine of so this is half bracket. Integrating that fast, we have 1 over sine of 39x plus 1 over 65 sine of 65x close bracket plus 1 over 1013 sine close curly bracket plus the integration constant c. And that, ladies and gentlemen, is our answer. Okay, so let's go to the next problem, number 15. So problem number 15 is the indefinite integral of e to the x times the arc sine of the hyperbolic tangent of x. And the first instinct is to substitute for that part. So we say let u be equal to arc sine of the hyperbolic tangent of x such that sine of u is equals to the hyperbolic tangent of x, and that means that cosine of u du dx is equals to the hyperbolic secant of x squared, and so cosine of u du dx is equals to 1 minus, okay, and this here is sine of u, so we have cos u over 1 minus sine squared u is equals to dx. So important part, but it's also crucial here to see that this is the same as cosine of u over cosine squared of u, which is the same as 1 over cosine of u. Okay, so let's see how. So our problem, e to the x arc sine of, and we saw that 1 over cosine of u du would be equal to that. Then let's see. So another crucial part is what is e to the x. So we want to express that. Okay. And so sine of u is equals to divide both or multiply both sides by e to the both numerator and denominator by e to the x. We have e to the 2x minus 1 over e to the 2x plus 1, which means that sine u e to the 2x plus sine of u is equals to e to the 2x minus 1. And that means that e to the 2x 1 minus sine u is equals to 1 plus sine u. And that means that e to the 2x is equals to 1 plus sine u over 1 minus sine u. So e to the x equals to the square root of over 1 minus sine u. And then this is the same as 1 plus sine u squared over 1 minus sine u, 1 plus sine u, is equals to 1 plus sine u squared over 1 minus sine squared u. So e to the x is equals to 1 plus sine u squared over cosine squared u, which is equals to 1 plus sine u over cosine of u. And so our integral e to the x arc sine of tangent of x is equals to 1 plus sine of u over cosine of u times, this is u times 1 over cosine of u du. So this becomes u 1 plus sine of u over cosine squared of u du. So our problem now has brought us to, okay, which is equals to u in bracket sec squared u plus tangent of u sec of u du. So this is the derivative of tangent of u, so derivative of secant of u. So this can be re-expressed as u times the derivative of tangent of u plus secant of u. And so using integration by parts, this being v, this being u, so we have u times tangent of u plus secant of u minus tangent of u plus the secant of u times the derivative of u, which is equals to u tangent of u plus secant of u minus tangent of u plus secant of u. So these are pretty straightforward integratable functions. The integral of tangent of u is the logarithm of cosine of u. Some people like to put absolute sign around it. The integral of secant of u is secant of u log of secant of u plus tangent of u. Okay, so we came to this point where we have u times the tangent of u and secant of u minus the integral of tangent of u plus secant of u. So this is the same as minus natural logarithm of cosine of u plus natural logarithm of tangent of u plus secant of u plus c. Now some people like putting absolute sign here, absolute, values there. But then we come to u tangent of u plus secant of u minus, using the rules of logarithm there, we have log of the product of these times this, which is the same as tangent of u times cosine is just sine of u. Secant of u times that, we have 1. We can put absolute value, that's okay. plus integration constant c. We know sine of u is equal to hyperbolic tangent of x. Okay, and we saw that e to the x equals to 1 plus sine of u over cosine of u. In other words, tangent of u plus secant of u. So this u here becomes arc sine of tangent, hyperbolic tangent of x, and this here becomes e to the x. So we have e to the x minus natural logarithm of we have 1 plus this, which is ex times cos of u, which is equals to the square root of 1 minus sine squared of u, which is tangent squared square root. So we can just easily just replace this with secant, hyperbolic secant of x, right? I mean, we don't have to simplify that further, and this is slightly different from the answer that was provided, but this is what we have gotten. So that's the answer. So e to the x times the arc sine hyperbolic tangent of x minus the natural logarithm of e to the x times the secant, hyperbolic secant of x. Okay. Yeah, I think that's it. Okay, let's go to the next problem. So problem number 16 just happens to be an indefinite integral of x times open bracket time of open bracket 1 minus x squared times cosine of x plus 2x sine x close bracket over the square of 1 plus x squared. So the important thing is to be vigilant, and you can see that. You can see this part here. So what that means that our integral is the same as the integral of open bracket 1 minus x squared cosine of x plus 2x sine of x times the derivative of negative 1 over 1 plus x squared, right? And then there's a half there, and then we have that. So using integration by parts, where as we've seen, this would be v and this would be u, we come to negative a half 1x squared cosine of x plus 2x sine of x over 1 plus x squared minus a half of 1 over 1 plus x squared times the derivative of, with regard to x, of 1 minus x squared cosine of x plus 2x sine of x. Okay, which is equals to negative a half minus x squared cosine of x plus 2x sine of x 1 plus x squared plus a half of 1 over 1 plus x squared, and then here in bracket we have 1 minus x squared negative sine of x, we're differentiating cosine of x, and then plus negative 2x cosine of x plus 2 sine of x plus 2x cosine of x, close bracket. And we see that that and that would cancel, and we are left with negative 1 sine of x. So this is the same as negative a half 1 minus x squared cosine of x plus 2x sine of x 1 plus x squared plus a half. So this and that have gone, and we have this negative interacting with this positive here, and we're left with sine of x minus, actually plus x squared sine of x over 1 plus x squared. And we can see that we can pull sine x out, and we are left with 1 plus x in brackets. So that is good. We're making progress. We can factorize things here and divide by 1 plus x squared, and that goes away. So we had negative a half 1 plus x, and then we have 1 minus x squared cosine of x plus 2x sine of x plus a half 1 plus x squared sine of x divided by 1 plus x squared. And so we have plus a half sine x dx negative a half 1 minus x squared cosine of x plus 2x sine of x over 1 plus x squared, and here we have 1 over 2 cosine of x plus the integration constant. Now we can combine everything in such a way that we would have in the denominator 1 plus x squared, and then we can pull half on this side, and we have 1 minus x squared cosine of x plus 2x sine of x plus cosine of x minus plus x squared cosine of x plus c. And so we see very soon that this and that go, and we have this and that, so we have 2 cosine x, 2x sine x. In other words, we have negative a half. In the denominator, we have x squared, and then we have 2 cosine of x plus 2x sine of x plus c. So this, and over 1 plus x squared plus the integration constant is our answer. So problem number 17, and this is a problem where I think there's a deviation from the answer that was provided. It says that the answer is 0, but we don't think that is the case, and we're going to show you why that's the case. So the first thing is, let's multiply this and get the quadratics in place. So we have 0, 1, and here we have sine of 5x squared minus 6x plus 1 times sine of 3x squared minus 2x. So sine of A, sine of B is the same as a half of cosine of A minus B minus cosine of A plus B. That is the identity we are going to use. And this is actually equivalent, so we just use the triple sign there. So our problem becomes integral from 0 to 1 of cosine of, if this is A and this is B, we get 2x squared minus 4x plus 1 minus cosine, and there's a half here, of 8x squared minus 8x plus 1. And we can express this further into cosine of 2x minus 1 squared minus cosine of twice 2x minus 1 squared minus 1. Such that if we say let u be equal to 2x minus 1, we come with, so let u be equals to 2x minus 1, means du dx is equals to 2, and therefore du over 2 equals to dx. Lower limit when x equals to 0, u will equal to negative 1. When x equals to 1, u equals to positive 1. And that means that we have half in place of negative 1, positive 1, cosine of u squared minus cosine of 2u squared minus 1 du over 2, so which is a quarter, cosine u squared minus cosine of 2u squared minus 1. Okay, and so this is not equal to 0. You can simplify it further, but it is not equal to 0. And it's hard to express this in a way that gives you the answer, unless these limits went to infinity. So we're going to stop here. For those of you who are curious, you can take this problem further. But we're going to stop here. Okay. So problem number 18 is actually a very interesting problem, and yeah, let's see how we may be able to solve it. So it's the definite integral from x equals to a quarter to the square root of 2 of 1 over x, open bracket, x to the power x and so on times natural logarithm of x minus 1. So I'm looking at this as my interest. So I would say let u be equal to x to the power x to the power x and so on, such that the natural logarithm of u is equal to what? Natural logarithm of u equals to natural logarithm of x to the x to the x and so on, which means that log of u is equals to x to the x on log of x. And so that also means that log of u is equals to u log of x. So, okay, let's see. Now, 1 over u du dx is equals to log of x plus du dx rather plus u divided by x. And what does that mean? It means that we can bring 1 over u minus 1 minus log of x du dx is equals to u over x divide both sides by u, so we have 1 minus u log of x divided by u squared du is equals to dx over x. So this is an important relationship that we need. And then the limits. So let's pull this. So we have u is equals to x to the power x, which is the same as u equals to x to the power u. Okay? When x equals to a quarter, u equals to a quarter, or let's express it in a way that is easy to appreciate. So this is the same as 2 to the power negative 2. Okay, so we try to figure out what value when we choose will give us this expression. So I'm thinking maybe half, because when we have half equals to 2, right, which is negative 1, which is cool. So when u equals to a half, the lower limit holds. What about when x equals to 2 to the power a half? In other words, u equals to 2 to the power a half times u. And that means when x equals to 2, we have 2 to the power a half times 2. So in other words, 2 equals to 2. So our limits will become lower limit half, upper limits 2. And then dx over x takes that form. So we have our problem, which is from a quarter to square root of 2 of 1 over x times x to the power x all the way times x all the way times that. Yet we've seen that when x or when u is said to be equal to x to the power x to the power x all the way, we found that 1 minus u log of x over u squared du is equals to dx over x. This is one thing. And when x equals to a quarter, u equals to a half. When x equals to square root of 2, u equals to 2. So our problem becomes that 2, and this is important, so we can pull it the other side, and we have u log x. We have chosen to keep that log x there for a specific reason. And in place of dx over x, we can have negative u log of x minus 1 over u squared du. You see this and this would cancel. So we have negative from a half to a half of 1 over u squared du, which is equals to 1 over u from a half to, which means a half minus 2, which is negative 3 over 2. And that, ladies and gentlemen, is our answer. So problem 19 is a definite integral from x equals to 1 of 1 plus open bracket 2026 plus 2x minus x squared minus 2 times 2026 plus 4x minus 4x squared over 2025 plus 2x minus x squared times 2027 plus 2x minus x squared times 2025 plus 4x minus 4x squared times 2027 plus 4x minus 4x squared. Now, I guess we see where whoever created this problem was going, and that is to express these as partial fractions and solve it. They suggested that the answer was 1, but we don't believe that's the answer, and we're not even going to try and attempt to solve it because it's a very convoluted problem. And the other thing is, I don't think the answer that was provided is the same as the actual answer. We will leave this as an option for whoever is curious to go ahead and solve it. But all the same, it's convoluted. I think the main goal here was to try and get somebody to separate this fraction into partial fractions and solve it. Anyway, so we'll go to problem number 20. So problem number 20 happens to be the definite integral from x equals to half to x equals to 1 of 4 to the x minus 1 times 1 plus 4 to the 4 the x minus 1, minus 1, and so on and so on and so on. So what I'm going to do is I'm going to try and substitute for this guy here. And so we'll say let u be equal to 4 to the x minus 1, meaning that log of u is equals to x minus 1 log to the 4, and so 1 over u du dx is equals to log to the 4. And what does that mean? It means that 1 over log to the log of 4, natural logarithm of 4, du over u can be used to substitute for dx. Next, when x equals to a half, that means that u equals to 4 half minus 1, which is 4 to the negative a half, which is 1 over square root of 4, which is a half. When x equals to 1, u equals to 4, 1 minus 1, which is 4 to the 0, which is equals to 1. So the limits remain the same. However, our problem changes a little bit. So our problem that is in the x domain, let's first of all write what is in the x domain. So we have a half to 1 rather of 4x minus 1, 1 plus 4 to the power 4, x minus 1 minus 1, 1 plus, and so on and so on and so on. And we say that in the u domain we have half to 1, and this here is u, and then we have 1 plus 4 to the u minus 1 plus, and so on. And here dx is du over log 4 times u. See, this and that cancel, so we pull out 1 over log 4, and we have 1 plus 4 to the u minus 1 plus 4u minus 1 minus 1. And we realize one thing. Let's rewrite what we got. So we have this problem in the u domain of 1 plus 4 to the u minus 1, open bracket, 1 plus 4 to the power 4 u minus 1, and so on, 1 plus. We realize that this is can solve this alone, so we have u, and then we have 1 over log 4 and we see that here we have 1 over 2 log 4 plus 1 over log 4 times the same integral, right? We can call it I. Okay, and which is interesting, because we can see if I is equals to 1 over 2 log 4 plus 1 over log 4 I. So there may be, so how we came to have I, and we have 1 over 2 log 4 plus I over log 4 I, 1 minus 1 over log 4 is equals to 1 over 2 log 4. So we have log 4 minus 1 over log 4 is equals to 1 over 2 log 4. And this means that I is equals to divide both sides by whatever we have as a constant on the left hand side. We have 1 over 2 log 4 times log 4 over log 4 minus 1. And that, so we have I is equals to 1/2 of 1 over log 4 minus 1. So rather, the answer is half of 1 over log 4, natural logarithm minus 1. So that's the answer for that last problem. You could have chosen to express it in form of a geometric series, and then you just have half times the common ratio being log 4, and as another way of solving it. Or you could just choose to represent this infinitely morphing or evolving integral, and you consider I to be the initial integral, and then you say, okay, there's an I that appears again after that first, integrating that first term, and then you'll collect the like terms and divide it the way we've done. However, there are many ways you could try to solve it. Whatever works is good. All the same, it's been an absolute pleasure solving these problems in the regular season of the MIT Integration B 2026. We'll move forward to the quarterfinals problems, and then proceed to semifinals and then finals. But yes, if you have any question, please don't hesitate to reach out to us. We do enjoy solving these problems. Until next time, bye-bye.